Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Gravity, gravity, gravity. Gravity makes things fall. But on this episode, I'm doing everything I can to defy gravity.
You win this one, Gravity.
From a hoop glider, to an egg drop, to a hover balloon, it's a gravity-defying dance party. All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max, we're going to be looking at gravity. What goes up must come down. Today, gravity is the force that makes things fall towards the ground. But just because it's a force of nature doesn't mean that we have to listen to it. No! Today on Science Max, Experiments at Large, we're going to use everything in the power of science to defy gravity. We are going to be making a hoop glider. Now, hoop gliders may not look like much, but they fly just like paper airplanes. Woohoo! And here's how you can make a hoop glider. Here's how you can make a hoop glider all your own. This is what you need. Index cards, scissors, straw, ruler, pencil, and of course, science tape, which is just like regular tape, except you use this kind of tape for science. So, here's how you do it. Take your index card and cut it into 3 equal lengths. Take 2 strips, and you take your science tape, and you tape those 2 strips and make a hoop out of it. And with the small strip, you want to make another hoop. Now, what you want to do is take your straw. Now, this straw has a little scoop at the end, and that's not very aerodynamic, so we're going to get rid of that. Ooh, maybe it was kind of aerodynamic. All right, now that we've got the straw, you have to align the hoop and the straw together. So here's what I like to do. Take some science tape and stick it on the straw, and then align it so that it's perfectly straight, and then stick it on. Looks straight to me, all right? The small hoop also has to be perfectly aligned with the first hoop. So again, put the tape on the straw first, then align them up, and then start looking down through it to make sure it's aligned. There. Once you have it all taped together, you're done your hoop glider. And it flies just like a paper airplane. Pew! Awesome. So that's what we're gonna do today. We're gonna, oh yeah, I gotta clean that up. We are going to max out the hoop glider. I'm gonna go meet Sonia at the Ontario Science Center, and we are going to max out the hoop glider into a giant version. We'll probably have to change the materials we use because, I don't think we can get a straw that big or cardboard, but still, we can figure it out. All right. Here I go. Aha!
Oh, hi, Phil. Yeah, what? Pardon? You want me to help you with an experiment? Okay. All right.
Oh, Sonia, I came in.
Phil,
You came in here? I
Are
came
you
in.
okay? Are you okay?
Yeah, I'm fine. Come on, let me show you. This is what I would like to max out. It was in my pocket when I fell, so
What is that?
It's a hoop glider. It was a hoop glider. So how do we max this out?
First, we're gonna need a larger tube.
To replace the straw, yeah.
Exactly, and we're gonna need 2 hoops. So we need something that's flexible, that will convert into a hoop.
Okay, that's great. So why don't we get started?
Sounds good.
All right, high fives. may recognize this. It is a spring. Yes, good for you. But did you know that springs can defy gravity? Whoa!
Gravity defy. Gravity defy. Gravity
Look at it fly! Defying. Okay, not exactly, but what if I was to hold the spring like this and let it go? What'll happen? It'll fall. Yes, it'll fall. That is true. But while it's falling, what happens to this end? Does it stay in one place? Does it go up? Or does it go down? Let's find out. I'll bring this in so you can really see it. Okay, ready? Watch close. Did you see? Did you? No? Okay, tell you what. We'll watch it again, this time in slow motion. See? The bottom doesn't move, and here's why. When the top of the spring is released, gravity and the tension of the spring are pulling on it. The bottom of the spring is being pulled down by gravity and up by the tension of the spring. These forces cancel out, stopping the bottom of the spring from falling until the top reaches it. Until there's no more tension, and then the top passes the bottom and the whole thing falls. That is how it works. But here is the real question. Will it happen differently with a longer spring? Huh? Well, I just happen to have a longer spring! Let's max it out! Bring it. Don't tangle it. So, now that I'm up high on this fire escape, let's test it out. Okay, 3, 2, 1, go! A longer spring still has the same forces working on it. The tension of the spring pulling it up and gravity pulling it down. No matter what size of spring, these forces cancel out for the bottom of the spring until the top meets up with it. So there you go, an almost gravity-defying spring! Hey, there's no door handle on this door. I guess I have to take the stairs. Whoa. Sonia and I are maxing out the hoop glider out of bigger and better materials. This is the largest tube I have, right? A giant ABS pipe and some bendable metal to make into hoops. Then we attach them all together and... Okay, big hoop is done.
And little hoop is also done.
Awesome.
Not bad.
Not bad at all. Super solid.
And that's the thing. We have pretty heavy material, so it might not fly as well as we'd like.
But something heavy can always be good, right?
Oh no.
That's what I'm talking about. See how solid it is?
Pretty
No
solid.
damage whatsoever. You want to test it?
I think we should.
Okay. I'm excited. We take our plastic and metal hoop glider outside to test it, and... Ready?
Ready?
1, 2, 3!
Huh.
It didn't really fly, did it? Sonia and I made a very solid design, but the problem with it became pretty obvious. Yeah.
It's just too heavy.
Well, that's what science is. Back to the drawing board. Here's something fun you can do if you ever get your hands on a helium balloon. Now, helium balloons float up, not because they defy gravity, but because they're lighter than air. It's because the heavier air around it actually falls past the balloon, and that ends up pushing the balloon up. But what if this helium balloon wasn't lighter than air or heavier than air? It was exactly the same. This is what I like to do. Just take a helium balloon with a long ribbon and a bunch of paper clips and adding a little bit of weight every time. And what we want to do is make this balloon neutrally buoyant. That means it won't go up or down, but it will be neutral. You want to check it every once in a while. Let's see, 3 paper clips is clearly not enough. 5 paper clips is, 5 paper clips is pretty close. It still might float down. So you want to take off just a little bit of weight, maybe about there. Watch this. You just take the balloon and you put it somewhere, and it stays. It stays put. It doesn't go up. It doesn't go down. It's attached to nothing. Now, let's max it out. Huh. I had a big balloon, and it was oh, there. Ha 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 ha! A giant balloon, and look, it's a great paper towel delivery device. Say, did you want some paper towel? Here you go. Science. Yeah, don't worry about Ramona. Just put them up high. Put them up, yeah, higher. Good. Hey. Grab it. Grab it. Gravity makes things fall. But where do they fall? They fall down. Oh. Towards the center of the Earth. Yeah? Gravity. It fell, didn't it? So, the Earth causes gravity, right? Well, yes, gravity. Oh, come on. Everything that has mass has gravity. Gravity. But the Earth has so much mass that the gravity produced by everything else is like nothing. I mean, forget about it. But let's say I was in space with this chicken. I would have gravity, and I could exert a gravitational force on this chicken. And if I get my angles right, I might be able to get the chicken to orbit me, like a moon. Behold, my chicken moon, huh? Gravity. But let's get serious. What causes gravity? We don't know. What we do know is that without gravity, there would be no universe as we know it. No you, no me, no chicken moon. I'd miss my chicken moon. Chicken moon, you what? Gravity. Like it or not, the universe wouldn't exist without it. You like the sign? I'll give you a good deal. Half off.
Back to our hoop glider, which was too heavy.
Here's what I don't get. This is heavy, but I can still pick it up and throw it.
Yeah.
An airplane is way heavier. I could never pick up an airplane, but that can fly.
And that's because airplanes have engines, so it has a constant source of thrust. When we throw it, we just have an initial source of thrust. So we're throwing it, eventually loses its energy, therefore,
it falls to the ground.
it
I
falls.
see.
So we need something that's light.
Light.
And something that's strong.
And strong. Okay, well, let's see what we can find.
All right.
Sonia and I try a plastic tube and some heavy-duty paper. We make hoops and attach them with some duct tape and run outside to try it out.
Hoop glider dance! Okay, 3, 2, 1.
That's pretty good!
That was
Pretty
amazing!
good.
Let's try that again.
Here we go.
I throw the hoop glider, and although it doesn't keep flying forever, it goes much further than our first version, and also further than I could have just thrown the pipe by itself.
Pretty good!
So we've done a good job of making something that flies. Why don't we make a couple different kinds out of different materials, and we'll see if we can get one that flies even better than this.
I think that's a good idea.
Yeah, okay, let's do it.
Sonia and I have created a pretty good maxed out hoop glider, but we wanted to see if different materials would make an even better one. Sonia made a much lighter version,
This time I used cardboard.
and I
I made
made a slightly heavier one.
Let's do it.
Okay, 3,
Yeah.
2, 1, go! Not bad. My turn.
Here we go.
Okay. Yeah. That didn't really go very far at all, did it?
No.
Okay, so now we can measure it against the one that we threw before.
And
to see,
that went pretty far.
This went pretty far to see if we've got a better design here.
Here we go.
Right? Wow.
Awesome!
So, heavy one, no. Light one, no. Interesting.
No.
This design seems to be the best one. I keep thinking about how you were talking about thrust.
Yep.
All the thrust that we can put in is just what we can put in with one throw.
Yeah.
What if we could give it more thrust than that?
How can we do that?
I don't know, like some sort of slingshot or something. Like it'd have to be a pretty big slingshot.
A pretty big slingshot.
you
But I
can
think
make
that sounds great, though.
I think make a big slingshot for this?
Why not?
Okay, high five. Let's do it. This is an egg. Eggs do not like to be dropped. Oh, fortunately, we can use the power of science to design something that'll keep the egg safe as it falls. Behold, my egg drop contraptions. The thing I really like about this experiment is there's no wrong way to do this. You can come up with any design you want and see if it works. This one here is a bunch of helium balloons. This structure is just to keep the helium balloons on so the egg can touch down very gently. Here it goes. Whoa. and the egg is unharmed, miraculously sound. That one worked really well. Success. This is a giant helium balloon that I think will work pretty much the same way, because I think this balloon will drop just slowly enough that the egg can actually just touch and nothing will happen. So that didn't work. And then there's this one, which has no slowing at all. It's all designed to just absorb the impact. And the idea is that the cone will crumple and absorb the force when it hits the bottom. Oh, no! Oh, no. I think it would have worked if it hadn't turned in the air, but it did, and, well, I guess the egg is completely broken. So I'd call that one a fail. This one is the parachute. You see the egg has been nestled into this foam container, and this is a parachute that will hopefully slow the egg down. Woo! Uh-oh. Whoa. Over, good. And that one seemed to work well. Yep, the egg is totally fine. The parachute worked. All right, egg drop experiment, totally fun experiment to do, but the question is, how do we max it out? And the answer is pumpkin drop. Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, gravity, but I'll beat you next time. I'm gonna get a broom.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. Delicious. Nothing is more important to have fresh than your seafood. It's what makes the difference between a fresh fish and one that isn't so fresh. If you live by the ocean, you probably know that the water gets high tide and low tide. Look closely, it's the same location. Amazing. But did you know that this is caused by the gravity of the moon and the sun? Say this cookie is the Earth. And this little happy fellow is me. Hello. And this string represents the water around the Earth. If we didn't have gravity to worry about, the water would all be equally deep around the Earth. But here comes the moon, this mushroom. Now, the moon has gravity, and that pulls the oceans towards it a little bit, like this. And that creates high tide there, and low tide here, and a little bump of high tide on the other side of the Earth. And as the Earth rotates and I'm on it, I experience low tide and high tide, and low tide and high tide. Very interesting. But there's another factor. The sun, or this lemon. Now, the sun also affects the tides, but not as much as the moon. Now, the sun does not affect the tides as much as the moon because it's much further away, but it still has an effect. If the sun was here, then the tides would be pulled away a little bit like that, and the tides would be less severe. But if the moon and the sun line up, like over here, you'd get a very, very high tide and very, very low tide. So there you are. That's how the tides are affected by the gravity of the moon and the sun. Delicious. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
Our maxed out hoop glider was working pretty well,
That was
Pretty
amazing.
good. Here we go.
but we could only give it so much thrust by throwing it. So we came up with the perfect Science Max solution.
Our giant slingshot.
We pull the bungee cord back and hook it onto our hoop glider.
I am ready to fire. Count me down.
3, 2, launch it! Very nice!
Our slingshot is amazing. By giving the glider more thrust, that is, more energy at the beginning so it's going faster when we launch it, the glider soars through the air and flies a long way.
That was great. So there you go. Giant hoop glider. Yeah, Science Max, experiments at large. Nicely done.
Nice.
What more could you ask for?
Well, it's my turn.
Hey, see you next time.
I'm a marker. Take 8. My goodness.
I play the wobble,
Wobble.
the wobble.
Forgot my line. Going back down.
Wobble, 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 wobble.
Hello? Hello? Hoop glider central calling. Yes? You were having problems with your hoop glider? Oh, what's wrong with it? Oh, you're using it as a phone? Yes, well, that's your first mistake, yeah. Today on Science Max, I forgot to tell you my name. My name is, I'll do it again.
This episode is all about mechanical advantage.
No longer will I suffer the weakness of human muscles.
Using the power of science to hurl pumpkins, pull cars, lift wheelbarrows, and, go back in time?
A trebuchet! A what? Trebuchet!
All on this episode of Science Max Experiments at Large.
Behold, Science Maximites! I am Filtron 2.0! I have changed myself into a cyborg to give myself super strength! No longer will I suffer the weakness of human muscles! Behold my awesome strength! Tremble in fear at my might! I may have to give myself some upgrades. Yeah, so, okay. Maybe I'll just give myself super strength the old-fashioned way, using the power of science! Today is all about mechanical advantage, like this fulcrum and this lever, transferring a lot of force over a short distance or a little bit of force over a long distance, and vice versa. We are going to be building a trebuchet. A trebuchet. So a trebuchet looks a lot like a catapult, but a catapult uses elastic force to throw something, and a trebuchet uses the good old lever. There's a lot of weight on the short end of the lever, and on the other side of the pivot is the long end, and we've got a sling here with a marble in it, and we put that down here on the ground, and then we let it go, and whoosh, whoosh, it throws the marble.
To build your trebuchet, here's what you need. Something to be your lever, like a pencil. Something to be your weight. I used batteries. You'll need to make a frame, and I use craft sticks and cardboard for that. A way for it to pivot, like a straw and a shish kebab skewer. Then you'll want a sling, which is a rope, and something to hold your projectile, like plastic netting. Finally, something to hold it all together, like glue.
Get your craft sticks, make some triangles with one craft stick sticking up. Then get your craft sticks and make a base which you will put on with your cardboard like that. Now you'll also probably want to make some extra supports that go off the bottom there like that. Then get your pencil and cut a piece of straw so that you can see right through it, and you can get a shish kebab skewer and you stick it through the straw like that, and that's your pivot point, your fulcrum for your lever. What you want to do is put your weights, I've used some batteries, you can use anything that's heavy, on the short end of the lever. That's important because a lot of weight here translates to a little bit of weight going a lot faster on the other end. So, a lot of weight on the short end, and then on the long end of the pencil where the eraser is, you want to take a toothpick and stick it into the top of the eraser and then cut it off so it's just like that. That creates a little hook that you put the loop of your string net on so that when it gets flipped around, the loop comes off and then throws your projectile that way. And then, of course, you need something that you want to fire. I like to use marbles, but gumdrops work pretty well because they're nice and soft. And you put it in and you pull it all the way down, all the way so it's actually resting on the cardboard like this, and then you let it go. And it fires. And there you go, a trebuchet. Now, if you want to research how to build one of these yourself, it is called a trebuchet. Haha, trebuchet. Wait, I can make it come up, but I can't make it go away. I don't know why that works like that. Anyway. So we need to max out the trebuchet. Let's see, I need an expert. Oh, Chris. Chris from Logix Academy has a trebuchet. Maybe we can use that one to figure out how we can max it out. And of course, because it's a trebuchet and it's maxed out, we want to fire something, so I thought we would fire, pumpkins. Let's go. Good luck, little pumpkin. Hey, Chris!
Hey, how's it going?
Chris from Logix Academy. I had a problem with the pumpkin. It kind of got larger than I expected.
It's okay, I think this one's bigger than what we need anyway.
Chris shows me a scale model trebuchet, one we can use to test a few ideas before building our maxed out version.
Go on
and
here.
you've got little mini pumpkins!
I know, don't get too attached.
The first is the arm length, getting the right ratio. That means how long one side of the lever is compared to the other. When talking about a ratio, you write it like this, 1 to 2. It doesn't matter what the actual measurement is, just that this side of the lever is 1 of that measurement and this side is 2, or 2 times longer than this side. And it turns out a 1 to 2 ratio arm wasn't great. Well, that could be better.
It could be better.
So we tried a 1 to 6 ratio arm. The 1 to 6 arm threw the pumpkin further, but not a lot further.
Better, definitely better.
Better? Then we tried a 1 to 4. Turns out 1 to 4 is the best arm ratio.
Whoa! That's pretty good.
Chris also had an idea about hanging the weights.
Because as you see here, these go straight down. And going straight down actually makes this spin even faster.
So when we do the big one, we should hang the weights off the end and not attach them to the end.
That's right, and that'll give you some extra distance.
Excellent. Let's fire this last one.
Okay, 3, 2, 1.
Whoa!
Pretty good.
Yeah. Okay, I wonder when we make the big one, do you think we can get it through the goalposts?
Oh yeah, I think we can do that.
All right, let's try it. All right. This episode is all about giving yourself super strength using mechanical advantage. Well, here's how you can use a rope to give yourself the strength of a superhero. Ha-ha! I am mechanical advantage using a rope man. To gain mechanical advantage using a rope, you need 3 things. First thing, a rope. I mean, obviously, that's a given, right? You know you need a rope. Okay, good. Then you need something to pull and something that will not move. What you do is you tie your rope to the thing that you want to pull. Then you tie the other end of the rope, you guessed it, to the thing that won't move. Now, you pull from the middle like this. And it's very easy to pull the weight. Why? Because of mechanical advantage. You're using a small amount of force over a longer distance. But what if the weight is heavier? Then you lengthen the rope. Now we pull from the middle and it's easier. Why? Yes, mechanical advantage. A small amount of force over an even longer distance makes it easier to pull the weight. Let's max it out. Mechanical advantage using a rope man, away! High above
of the city, mechanical advantage using a rope man surveys the town looking for someone in trouble. There's someone.
Oh, my minivan broke down and only 10 feet from my parking spot. If only there was someone who could help me.
I'll help you.
Mechanical advantage using a rope, man. I'm saved. Maybe you should try giving yourself some mechanical advantage using the rope. Mechanical advantage using the rope, man.
Yes. Well, I was coming to that. So I have this really long rope, and I tie one end to something that's not going to move, like a tree. Or a steel coil, if you happen to have one. And then I take the other end, and I run all the way back, and I attach this end to the van.
I call her Bessie.
Then I go to the middle of the rope, and I pull on it sideways like this, giving myself a huge amount of mechanical advantage.
Oh, it's working! It's working!
Pulling.
Mechanical advantage using a rope, man! You're doing it!
Ha-ha!
Well, gee willikers, you did it, mechanical advantage using a rope, man. You pulled the whole van.
And that's how you can use a rope to give yourself super strength. I am mechanical advantage using a rope man. Based on what we've learned from our small-scale trebuchet, Chris and I made a maxed-out version.
All right.
This, I think, is
Wow.
as big as we could possibly be expected to build this.
This is huge.
We have the length of our arm, which
Right.
is important.
Yes, and we've got to add weight here, so
Yeah.
we're gonna like loop this in. Whoa!
Oh, I guess that's because I took the weight off.
Yeah.
So, the arm is 4 times longer on this side of the lever
Right.
than on that side of the lever.
Right. So this arm goes 4 times faster than that side,
But
but we're gonna need a lot of weight.
like our small version, we needed to hang weights on the back of our trebuchet. So I got a rope and put some weights on. But because our new version is so maxed out, we need a lot of weight, which I needed to get on a rope and drag it over. Okay, almost there. And I needed to lift it onto the arm. I lift it. You know, maybe we should do this together. And you take one end. And we lifted it.
That's gonna be a problem, Phil.
I'm kind of glad that happened because there was no way I was going to be able to lift that.
I know, it was way too heavy, and we need something stronger that can still hold the weight and still give us the hinge that we want at the top.
And once the weight's up there, if the rope broke,
That would be bad news.
that'd be big time bad news. Okay, so we need a new solution for getting the weights on the trebuchet that is not.
Not rope. We need something
Not rope.
stronger and hopefully that still has the hinge on it up here.
Maybe we have some sort of bar system that we could hang.
Yeah, I'm thinking metal.
Yeah, metal, definitely metal.
Definitely metal.
Metal is better than rope
I think so.
for holding a whole bunch of weight. Okay, let's get that done.
Let's do it.
All right, I got some metal over in the shop over here.
Okay.
Come on down to Sal's Science Shop. I am Sal, and this is my science shop. You want levers? I got the best levers around. Little levers, big levers, all drastically reduced. If you can find a lever anywhere else for less, then you gotta tell me, because I didn't know anybody else was selling them. Come on down to Sal's Science Shop, your one-stop shop for science. Hey, you want some levers? Well, boom, have I got levers. What class would you like? What's that? You didn't know that levers have different classes? Well, there are 3 different classes of levers. First class, business class, and coach. No, first class, second class, third class. It's pretty straightforward. And what do we need when we have a lever? We need a load, we need a fulcrum, and we need a lever. Ha-ha! First class lever, the fanciest of levers. You got your load on this end, you got your fulcrum right here underneath, and then you put some effort into this end, and wow, look how easy that is. Ha-ha! First class. What kind of thing works like that? Oh, I don't know. How about this trebuchet you've been spending all this time watching? First-class lever right there in front of you. Second-class lever. Look, there's a load right here in the middle. The fulcrum's on this end, and you put your effort into this end, and you lift it, and look, it's a second-class lever. Huh? How cute is that? But what kind of thing works like that? It's like a wheelbarrow. The fulcrum is the wheel. The load goes in this, I guess this is the barrow, and then I lift with the handles. Huh? Look at that. Ha! Lever! Third-class lever. You got your load on this end, you got your fulcrum on this end, but where is the effort? The effort's in the middle, and it pivots while you move it. Huh? Where you gonna get that kind of crazy contraption? Salad tongs! Salad tongs! Salad tongs. Look, you put the effort in the middle there, it pivots on that end, and you have the load there. And there you go. First class, second class, and third class levers. Whatever your mood, we've got the levers for you.
Chris and I had some trouble getting the weights on our maxed out trebuchet.
That's gonna be a problem, Phil.
So we had to come up with a new system. A metal bar that pivots on the bottom of the lever arm. It's got lots of spots for weights, and we could lift the weights one at a time to attach them all. We start out with
255 pounds. How many kilograms is that?
113.3 continues.
Yeah, that's what I got too. All right, that's definitely enough weight, right?
Definitely.
Okay, let's fire a pumpkin.
Let's do it.
this trebuchet works the same as the other models, but because it's so much larger, we really need to haul on the rope. We attach the arm to a quick release, which allows us to hold it in place until we're ready to fire.
Oh, here we go.
Okay.
3, 2, 1.
Whoa!
Oh!
Whoa!
We launched a bunch of the same size pumpkins and got a pretty good idea of how far we were throwing them.
Okay, you know what? We should leave this here so that we know how far that last pumpkin went.
And then try to beat it.
And then we try to beat it. We haven't gotten through the goalposts.
It seemed to handle the more weight pretty well. I think we can add even more. What do you think?
I think we should add all of the weight. This is Science Max. This is not like Science Minimum.
Let's max it out.
We
maybe.
totally maxed it out. Okay, all the weight.
All
the weight. All the weight.
Max Historica.
Good morrow to you! I am Lord Fillington IV, and welcome to my medieval castle! My father, Lord Fillington III, had his castle besieged by catapults, and he had to share his prized collection of snow globes. Well, I, Lord Fillington IV, have made a few improvements. First, was forgetting about snow globes. Those are so last season. I collect limited edition Science Maximals stuffed toys. And I've collected them all, and I'll never share. Hello? That Lord Fillington has been hogging all the limited edition Science Maximals, and he won't even trade. I mean, look, I've got 3 floofers, and all I need is a Fricto. But he won't trade. Surely you can trade. Never. I have all the Frictos, and I'll never trade. That's it. Time to build it. Oh, you're gonna build a catapult and knock my castle walls down? Well, I've learned a thing or two from my father. I, too, have catapults. Release!
Fortunately, we've got a new invention of our own. A trebuchet.
Oh, fiddlesticks. They have a duck pate.
Trebuchet.
A what? A Mother's Day? A Hudson's Bay? A Cabernet? I can't hear you. You've got to come closer. Release!
The trebuchet was the best thing around right up until the invention of gunpowder. It could throw farther than anything else, even catapults. What you do, you see, is you put something in there, and then you put a big weight up there, right? And this goes down, that flies around and flies over the castle walls, all from far enough away where he can't get me with his catapults. And it works like this. 3, 2, 1. No, didn't that make it? It's too high, it's too high. Ah! All right, I give up. I'll trade. Oh, that's quite nice. I like that. Oh, and that's how trebuchets were used in history. Sort of. Our giant trebuchet launched a pumpkin pretty far.
Very cool.
But now it's time to max it out further by adding even more weight. All the weight, all the weight, all the weight. So we increased the weight to 425 pounds. That's a lot of weight. Okay, are we ready?
I think so. I can't wait to see what this thing does.
I can't wait to see how heavy it is to pull. Turns out pulling that much weight using our rope was really tough, even with the mechanical advantage of our lever. There we go. We found another pumpkin of the same size, but then we started having another problem. 3, 2, 1, go!
Whoa! Look at how high it is!
What? Whoa! Go!
Whoa!
What? Whoa! So, I think we're going a little too high.
Yes.
It was almost straight up. How far the pumpkin goes all comes down to when the rope slips off the pin at the end. If the rope slips off too early, the pumpkin goes up and not very far. Too late and the pumpkin goes straight, which means it'd hit the ground sooner and doesn't go as far. A 45-degree angle is just right. And how do you adjust it? By simply bending the pin. 3, 2, 1.
Whoa! That's great. Great.
That went way farther than 60. We should have had another sign.
I don't even know how far that went.
Yeah, there you go. Science Max, experiments at large, trebuchet. So, one of us has to clean up the pumpkins and the other one has to put the trebuchet away.
Right.
Pumpkins! Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're gonna be looking at water. But water is very heavy, but that's okay because we need it to be heavy for this experiment to work. I don't know if I need that much of it though. Maybe I can get, here we go. Yeah, that's probably all I need. Today, we're going to be building a water-powered car. You'll need a base for your car, like this styrofoam, water bottles, shish kebab skewers, straws, scissors, elastics, paper plates, tape, a square of paper towel, modeling clay, vinegar, baking soda, water, and glue or a hot glue gun if you have an adult to help you, and... yeah, I know, this one is pretty involved. That's why you should go to the website for step-by-step instructions. Take your paper plates and glue 2 together to make a wheel. Then make 3 more. Wrap elastics around your base and then tape straws on the bottom. Trim them down, maybe about that much. Then take your shish kebab skewers and push it through a water bottle cap to make a hole. Then stick one wheel on, put the skewer through the straw, and do the same thing on the other 3 sides. Then take the water bottle cap and get an adult to help you make a perfect hole in it so that it fits your straw. Then use some modeling clay and hot glue to seal the straw and the cap so it's airtight. Attach the water bottle to the base of your car, then fill it with some water and vinegar. Next, you'll want to wrap up a spoonful of baking soda in the square of paper towel so you can make a little package. Finally, stick something underneath the underside of the bottle to raise the end up off the base. Bring your cap and then go outside. Here we are outside. Yeah, I know, we're not really outside, but I have a science lab and you probably don't, so I highly recommend you do this outside. And don't forget your safety glasses. Now, this is why we make a little packet of baking soda, because we want to delay this reaction as long as we can. So I like to hold it there. We'll hold it there with one finger so I can get the cap ready, because we don't want it to react until we can get the cap on and then kink the straw to keep the pressure inside till we're ready to let it go.
Then at the last second, you want to drop that packet in and quickly cap it and kink the straw. And woohoo! Woohoo! Haha! There you go, a water-powered car. Now, I know what you're thinking. You're thinking, Phil, wait a minute, that's a vinegar and baking soda-powered car. Well, kind of. The vinegar and baking soda create a gas, and that gas creates pressure in the bottle, and that pressure forces the water out of the bottle. But it's the water leaving the bottle that creates the thrust. The water going that way pushes the car that way. Newton's third law, every action has an equal and opposite reaction. So what we're gonna do is max out the water-powered car. Figure out how to get water going that way so we can go that way. But we means me and someone else. Who can help me? Oh, I know, Anthony from the Ontario Science Centre. He'd be great at this. Hopefully he's not busy. We're gonna max out the water-powered car. Ha. Anthony! Phil, sorry about that. Did I scare you?
Don't worry about it.
How you doing?
Awesome, thanks.
Great. I was wondering if I could get your help on an experiment.
Yeah, okay. Which one?
I'm building a water-powered car. It's gonna be great. It's Science Max headquarters. I'll show you.
Phil?
Anthony, I'm here.
Whoa, Phil, where are we?
Oh, this is the parking lot for Science Max headquarters. So,
Okay.
today,
Yeah.
I want to max out the water car.
This thing is awesome.
Yeah, so what you do is you use vinegar and baking soda,
Yeah.
and you pressurize this container, and,
Okay.
and the water shoots out that way. So the car goes this way.
Newton's third law. Every action has an equal and opposite reaction.
Yeah, you know your
Okay,
stuff. This
okay.
is why you're here. This is because I could really use your help and advice on how to make this bigger.
Okay, so we're gonna need a bigger tank to pressurize. So this, what about something like this?
So we need something that can hold pressure. Do you think this would work?
I don't know if we'd wanna...
And we'd have to put like pressure fittings on the barrel, like cut a hole
Yeah.
and weld them on. I don't know if that's...
Something tells me this wouldn't work, so we
Okay,
need,
sure. I got some other stuff over there maybe that we could use.
Check this out. Yeah, I think this would work. This would work a lot better.
Well, this is my stand-up wash tub base.
Your what?
So
Yeah.
we'll reuse it. Yeah?
Okay, you know what I'm thinking
Yeah.
now, though? I know
Yeah.
this. The problem is, I think this is like an oil drum, right?
It
And-
is.
And,
It's an oil tank from a house.
and these things are not built for pressure.
You can get water tanks that you pressurize.
Like hot water heaters, yeah, you can pressurize. They're built for that stuff. You pressurize them in your basement, and then the water travels up to like
the top
your
floor.
shower
That
or
makes,
something like that.
So all we need to do is get a pressurized water tank,
Okay.
put water in it, put pressure in it, and put it on wheels. And then we open the valve and it goes, right?
That sounds amazing.
All
yeah,
right.
let's get to it, man. Okay. we
I
need
got
to-
some water tanks over here in this corner of the parking lot.
Seriously?
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. When you're a professional chef like me, you spend lots of time perfecting the perfect recipes. I know my way around a kitchen, and today I'd like to show you one... That's not the fridge. Oh. Today I'd like to show you one of my favorites. Quail truffle gazpacho cakes on a plate of ice. Beautiful. And here's how to make it. Take some quail, some truffle, and some gazpacho and put it into a cake. Delicious. And here's the interesting part. How to make the plate of ice. Ooh, how did I do it? Well, I tried many different methods, and none were very successful. But now I let science do the work for me. So here's what I do. You see, I've got my large block of ice, and I've got a fishing line over the top, and on the bottom, I've got 2 heavy weights. Now we wait.
The heavy weights put pressure on the fishing line. This pressure melts the ice where it's pressing down. As the ice melts, the fishing line moves through the block of ice and eventually cuts its way through.
There we are. My hours of waiting have almost paid off. You see, I've got a perfect line through the ice, and I stopped it just before it finished. It's the pressure of the line on the ice that makes it work. The same thing happens when you use ice skates. You see, it's a very thin line, and your body weight presses down on the ice, melts it a bit, and that allows you to glide across the ice. It also allows me to just pop this off. There you are, you see? Perfect plate of ice to put my delicacy on. Let's just try that now. There we
So I've joined Anthony and we're going to max out our water-powered car. Our small design works by creating gas, which creates pressure, which forces the water out of the bottle, creating thrust. Our new plan is to get a water tank, put it on wheels, and put water in it. Then we use an air compressor to pressurize the air inside. When we open the valve, the water is forced out this way, which causes our water car to go that way.
Okay. Haha! So, water car, maxed out version,
Huge.
water tank.
And filled with lots of water and lots of air. Too. Yeah. Pretty good, right?
Whoa.
It's a lot of it. So,
Did it mess up my hair?
no, you look fine. You look great.
Okay, good.
Now, the only thing left is we just gotta open this valve here, right?
Yeah. You want to do the honors?
Yeah, let's do it. Okay.
Okay, here we go. 3,
2,
1, go!
We open the valve and our pressurized tank moves forward. The air pressure in the tank forces the water out with enough force to move the tank.
Awesome! That was awesome!
That was a great run, yeah.
That's amazing.
So, pressurized water tank on wheels.
Totally worked.
Totally works.
Total success, yeah.
So, because this is Science Max, the only thing we can do now is make it bigger.
Bigger,
right?
exactly,
Okay.
yeah.
So, problem is,
I don't think we're gonna find a tank bigger than this one.
Yeah.
So,
because then it would be too heavy, right?
exactly,
Much
way too
bigger.
heavy. Maybe what we can do is just get a lot more water,
Okay.
and then we find a way to pressurize the water.
Oh, so don't pressurize the whole tank, just the stream of water that's going out
As
of
it
the tank.
comes out, exactly. Something kind of like a fire hose.
A fire hose, right.
So
we take a big container of water,
right?
and I guess we would need a pump.
Yeah, like a pump would be perfect.
So then we suck the water out of the container, put it through the pump to pressurize it, shoot it out of a fire hose.
And then our car goes flying.
Goes flying.
Okay.
Yeah, let's do it.
Yeah. All right. Amazing.
When water is going fast, it has a lot of force. This is a power washer. It's made for cleaning concrete and wooden decks, but it doesn't use soap and it doesn't use heat. It only uses the power of water. Let's try it out.
The power washer creates a stream of water that is moving really fast. It has the force to clean concrete, strip the paint, or even the Science Max logo off wood. But how do I max out the power washer? What's the most ultimate use I can think of?
Power washer pumpkin carving.
The power of the pressure washer creates a stream of water strong enough to make short work of my pumpkin. Power washers may only shoot water, but they can be dangerous, so don't try this at home.
Yeah, science!
The Wizard Academy. All you have to do is demonstrate true magic, and you'll be granted entry.
Send in the next candidate. Oh, no, not Overwhelmo.
Did someone say Overwhelmo?
No, wait, no, next. No, not that. Okay, good, okay.
Behold, it is I, Overwhelmo!
Welcome back, Overwhelmo. If you can truly demonstrate magic, you may join the Wizard Academy.
A glass of water! No, wait, that is not the whole trick. Okay, hold on. Okay, and this, a waterproof playing card. I put the card on the glass and flip it upside down, and then I say the magic word. The magic word. And behold, magic! Yes?
Is that it?
Yes?
Well, it's not magic.
It is defying gravity.
Nope,
The water would fall and the card would fall to the floor.
it's not magic.
This is magic.
No, it's science.
Horse feathers.
Look, the reason the water doesn't come out is the air at the top of the glass keeps it held in by suction. More air would have to get into this glass to decrease the suction, and because the playing card is keeping a seal on the glass, the suction of the air is holding the weight of the water up.
Boulder Dash.
All right, look, let's do a little experiment then, shall we? Let's move the playing card just a little bit from the edge of the glass. You see those bubbles?
Yes.
That's bad news. Science, not magic.
Well, I will return, and then you will see your mind will be melted by the. No, that's not my music. You will rue the day when that's not my new hold. Overwhelmo shall return.
Our maxed out water car worked pretty well. Now it's time for something even more maxed out. We start with a giant tank on wheels, we add a pump to pressurize the water, and a fire hose to shoot it out the back. What's more, this version is big enough for me and Anthony to ride.
Water car!
So this is the more super improved water car. This tank holds 1,000 liters, and right now it has 720 liters of water.
We have a pump, that's right, our water pump. So the idea is we take the water from this container out through your hose, really pressurized, going really fast that way. Our car goes really fast this way.
All we gotta do is just turn on the pump, and we're ready to go.
So we fire up the pump and the water stream comes out really strong. So strong I can barely hold on to it.
Here we go!
But even so, there's a problem.
What's going on back there? I got it! Yeah.
Nothing happened.
No, nothing really. Well, something happened. We got wet, but it didn't really.
It's too heavy.
Too heavy.
So you're on it and I'm on it. That's a lot of weight. We don't ride it. That's something.
Yeah.
Also, this is kind of going crazy.
Yeah, because if nobody's holding it, it's just gonna flap around.
So we'll have a brace here.
Yeah.
Shoots it that way. That's good.
And then we'll need, I feel like we'll need something to kind of propel it. Maybe a better propulsion system. Kind of like one of those steamboats.
So we put a big paddle wheel here.
Exactly.
And we aim it, I guess we aim it down
at the, yeah, exactly.
like that.
And then,
at the paddle wheel, and then the paddle wheel spins, and that propels the car,
exactly.
right?
Right.
Okay, well, we can do that. Let's do it.
Sounds good, yeah.
Together. You know what? I have a paddle wheel because I had a failed hydroelectric.
This is called flyboarding. Wow. Whoa. Powerful jets of water are being shot out from this board at my feet. Whoa.
The engine on the watercraft behind me creates the water pressure, which travels up the hose and through the jets. The force of the water is strong enough that I can use it to fly around. So what's the difference between this and a water car? Well,
We don't have to take that much water with us because it starts in the lake and ends up in the lake. So the only water I have to carry is in the hose that goes up to the platform. Woo-hoo!
flyboarding is lots of fun, but it takes some practice to get it right. Balancing on jets of water isn't easy, but I got the hang of it.
It's all due to Newton's third law. For every action, there's an equal and opposite reaction. physics! Woohoo!
Our maxed out water car didn't work so well. The main reason is that much water is heavy, 720 kilograms.
Yeah.
So Anthony and I have a plan. Rather than rely on the force of the water going straight out the hose, we're gonna put a water wheel on the back of the water car. A water wheel works by catching water in the segments of the wheel. The weight of the water on one side of the wheel causes it to start turning. But we're gonna use the weight of the water and the pressure of the water. Hopefully, both combined will be enough force to turn the wheel, which will drive our water car forward. A little construction, and we have it ready to go.
Okay, so here's the latest version of the water car, water wheel.
Yeah.
All right.
Yeah, there we go.
We try it out, but there's a problem. The trick with the water car is the water itself weighs a lot. Every liter is 1 kilogram, so our 720 liters we start with is way too heavy to get the car moving in the beginning. But as the water gets pumped out, there's a sweet spot where the weight is low enough the water car might move. But then there's only a little water left, so it's a balancing act. We fill it again and see if we can come up with a plan.
Okay, new and improved version, only half full. So the idea this time is because we're starting with it only half full, right?
Yeah.
Then it'll begin to go a little easier because it won't have as much weight as it had the last time we did it. And Phil, yeah?
I can't even move this thing.
What?
I think there's too much fuel. There's too much. Yeah, there's no way we can move this. There's no way this is gonna be able to move
Even
on its own.
half full, you
Even
can't
half full,
move
I
it.
think we need less fuel. We gotta get down to like maybe like a quarter or something like that.
The thing is, we ran it from the full tank last time, and it never
Okay.
moved at all.
What if we gave it like a push to kind of help it get over that little bump of energy?
Ah, so give it the first push when it's still got a bunch of water in it. We give it a bit of a push, and then maybe it'll go in its own.
Exactly.
Okay.
Wanna give it a
Yeah,
go?
absolutely. Let's do it.
We start the pump and wait for the amount of water to get to just the right spot. Then we give it a push while it's still kind of heavy to start it moving. Sure enough, that push makes all the difference.
Yeah, it's working!
The water car is light enough to roll, has some momentum to keep it going, and the force of the water coming out the pump is enough to keep it moving forward on its own.
Still going! Woo-hoo-hoo! All right!
Amazing! Yeah! Look at it, man. This thing worked like a beauty.
It worked all. It went all the way.
Yeah!
Way to go! The water car, finally a success. It was the push.
It was the push. That's all we needed to get it going.
A bit of a push to get it going and a lot less water, and there you go. It totally works. All right, you want to do it again?
Absolutely.
All right, here we go.
Okay.
See you next time on Science Max Experiments at Large.
So much easier to push it without any water inside it.